In this video, we're going to take a look at the end behavior of power functions. The text doesn't really spend any time on this, and that's because I think it's a review from pre-calculus, but I think it's important enough that I want to take some time out to review this. So a power function is just a function of this form. Y equals f of x is a multiple of x to the n. So a there, our coefficient, that's allowed to be any real number. The exponent n is going to be a positive integer. So remember that fancy symbol z means integers with that superscript of plus. That just means positive integers. And we're going to start with some specific examples. I'm going to first of all start with a being 1. We're just going to make the coefficient 1, so we're just looking at x to the n. So if I'm looking at f of x equals x to the n, I can basically break those functions up into two types, where n is even and when n is odd. Let's start with n being an even positive integer. So we've already stated it's got to be a positive integer. Now I'm adding to that it's got to be even. Okay, so I'm going to just take a look at the graphs and see if we can't evaluate the end behavior that way. So the first positive even integer that I have would be 2. So let's look at y equals x squared. Well, I'm familiar with what that looks like. That's just a parabola like so. And looking at the graph, it's hard to realize that it's going to be over here at some point because it looks like it's getting so steep. But this arrow says it's going to keep going up and to the right, and it's just going to be really, really high up by the time it's moved over this far to the right. That arrow is going up and right, and that arrow is going up and left. So I can say that the limit as x goes to infinity of x squared is infinity, and the limit as x goes to negative infinity of x squared is also infinity. Doesn't matter whether I'm going left or right, the function goes up. All right, let's take a look at another even power. The next positive even number we have would be 4. So let's look at y equals x to the 4th. The graph of that actually looks very similar. There are 3 points that are going to be on the graph of any even power of x: the origin, the point 1, 1, and the point negative 1, 1. Now it's tempting to say that x to the 4th is always going to be bigger than x squared because it's the bigger power. That's not quite true. Between 0 and 1, if I look, for example, at 1/2, 1/2 to the 4th would be 1/16, whereas 1/2 squared is 1/4. If I have a number between 0 and 1, taking it to a bigger power actually makes it smaller. So between 0 and 1, x to the 4th is lower down. And of course, even powers are examples of even functions. They're symmetric about the y-axis, so I'm going to have a mirror image of that over there. But once we pass 1 on the right or negative 1 on the left, now taking x to a bigger power is going to give me a bigger result. So now I can see x to the 4th is higher up than x squared once we're to the right of 1 or once we're to the left of negative 1. But it's basically the same end behavior. Okay. So the limit as x goes to infinity of x to the 4th is infinity, and the limit as x goes to negative infinity of x to the 4th is also infinity. Okay. Now, the next even power would be y equals x to the 6th, and it's going to have the same basic shape. It's going to pass through these same 3 points. Between negative 1 and 0, and between 0 and 1, it's more shallow, and it's more flat as it passes through the origin. It's not completely flat, but flatter. But then it's going to become bigger. So that, oh dear, that's hard to see. To the right of 1, the red graph, which is x to the 6th, is higher up than the green graph, which was x to the 4th, is higher than the black graph, which was x squared. Okay. So basically, even power functions are going to go off to infinity on both sides, at least unless I modify them with a coefficient that changes that. Okay. So I can actually say if n is even, okay, at a positive integer, then the limit as x goes to infinity of x to the n is infinity, and the limit as x goes to negative infinity of x to the n is also infinity. Okay. Now, how does the coefficient a affect that? Well, if a is positive, that's not going to change things at all, because I know that multiplying by a positive number is just going to stretch or shrink things vertically, but stretching or shrinking is just going to make it go off to infinity faster if we stretched it and slower if we shrunk it. Okay. But if a is negative, I know that multiplying by a negative number would perform a vertical flip. So that, for example, negative x squared looks like this. And the same would be true for any negative multiple of any even power. Okay. So basically, if a is negative, it's going to flip the graph over vertically, and that just changes the end behavior by reversing its sign. So a negative multiple of x to an even power is simply going to go off to negative infinity on both sides. Excellent. Let's take a look now at odd powers. So we're going to look at f of x equals x to the n. N is going to be an odd, but still positive integer. Okay, so we're still talking about power functions with positive integer exponents. Okay. So the first one that I have is just y equals x to the first. That actually counts as a power function, and that's just a line of slope 1 through the origin. This is the only power function we're going to have that doesn't curve in some way, shape, or form, but that certainly counts. And just looking at that graph, I can see the limit as x goes to infinity of x to the first is infinity. Because here the x and y values are the same, so they've got to be doing the same thing. And so the limit as x goes to negative infinity of x to the first is negative infinity. Now, my next odd power would be y equals x cubed. Now, just like with the even powers, there are going to be 3 points, 0, 0, 1, 1, and this time it's negative 1, negative 1. Those are going to be on the graph of any odd power of x. Okay. And again, we're going to see a similar pattern. Okay. Looking on the right side where x is positive, between 0 and 1, the bigger power is actually smaller. So x cubed is smaller than x if I'm plugging in a fraction between 0 and 1. But once we pass 1, x cubed is bigger than x. And so it's going to be going off, that's a nice smooth graph. There we go. It's going to be going off to infinity. It's just going a little bit faster. Okay. Excellent. Now, odd power functions have rotational symmetry, or symmetry about the origin. What that basically means is if I were able to take this and flip it upside down, just rotate it 180 degrees, it would look exactly the same. Now here, because I'm dealing with negative y values, That means between 0 and -1, x cubed is actually the bigger function because it's less negative. It has the smaller absolute value there. Okay. But then once we pass -1, it has the bigger absolute value, which means it's lower down. So it's going to -infinity, but faster. Okay. And if I were to look at x to the 5th, I would see a similar pattern. All odd powers behave basically the same. So we can say the limit as x goes to infinity of x to the n, if n is an odd, again, positive integer, this is just going to be infinity. So we go off to the right, we go up. But the limit as x goes to -infinity of x to the n is -infinity. Okay. So if the power is even, it's the same end behavior on both sides. If the power is odd, it's opposite end behavior on both sides. And of course, as with the even powers, the sign of the coefficient can reverse the end behavior. If I multiply any function by a negative number, that performs a vertical flip, and so that would simply reverse the sign of the end behavior.